Hello, so welcome to the lecture recording for MRI the Basics Chapter 14, which is called Pulse Sequence Diagram for UCSF BI 201. First, our MRI picture of the day distraction here. This is a contrast enhanced scan MR angiography. So what this means is the subject had a gadolinium chelate injected intravenously, and this agent primarily, at least at first, shows up in the blood vessels. It's a T1 shortening agent, so it makes the signal very bright on T1 weighted images, and so you see these really clear depiction of the blood vessels. You can also see some of the agent going into some other organs as well. It will get into some tissues. And then you can also note on this image is what's called a maximum intensity projection. So this is not a single slice, but a projection, a combination of the maximum signal across multiple slices. Okay, so for this chapter, we have these three goals. I like this quote from the book. It says, a pulse sequence diagram is to an MR scientist as sheet music is to a musician. And I would completely agree with that statement. Whenever we're talking about or investigating a new pulse sequence or changes to sort of any MRI experiment, the first thing you're going to show is going to be the pulse sequence diagram. And so first couple of the learning goals are related to components of the pulse sequence diagram that I've included, but we have not explained yet. So we'll describe the purpose of these gradients that we have not covered yet. And then there's some changes we need to make into the pulse sequence diagram, or how we think about our imaging gradients when we have spin echoes. So here's a couple of various pulse sequence diagrams, and I'm going to highlight, a few pieces here that may look, a little bit abnormal in terms of what we covered. So one is the effect with slice rephasing. That's referring to this little chunk of gradient, this negative GZ. And we're going to first explain that. We're also going to cover so-called crusher gradients. In this, there's a couple in this diagram. There are these two around our spin echo pulse. And then we're also going to look at the effect of 180-degree pulses or spin echo on gradients. So here you want to note a contrast between these two sequences. There's actually a different polarity of the frequency encoding gradient. And in fact, both of these will accomplish the same thing. How they do that is what we're going to try to explain here. So starting out with slice select refocusing. So I'm going to give you sort of a intuitive explanation here, and we'll leave it at the level of basically what I'll cover here, and then I'll provide you a resource if you're interested for more details. So if we look at our RF pulse, our slice selective RF pulse at time 1 here, we have no, and what I'm showing in the middle here is the transverse magnetization in the slice direction in Z. So we start off no transverse magnetization, no flip angle. We at the end of the pulse here, now we create some transverse magnetization. We can annotate here. I've specifically drawn this to only exist over some limited distance over our slice thickness. But it turns out that at this point, there's actually going to be a little bit of dephasing due to the magnetic field, the gradient applied during the RF pulse. And so what this slice select rephasing a refocusing gradient does is it basically unwinds this gradient. So it's going to do some add some phase or some rotation that depends on the spatial position, and put all the spins across our slice in phase. If we left things at time 2 here, we would, as you see, we'd have things a little bit out of phase, or they can be actually even more extreme than this, and we'd have reduced signal. So this refocusing gradient is very important for our excitation pulses to get the most signal possible. A couple of rules of thumb here. If we take the time here at the center of the RF pulse, what we actually want is this area here is equal to this area here. And if we do this, this is the condition under which we'll get the refocusing. Okay, so this is why you'll see this gradient drawn with, again, this half gradient area, but reversed polarity at the end. And if we don't do this, we're going to lose signal. And so these animations here show a slice selective pulse. And what you notice at the very end is that, and it's probably easiest to see on the rotating frame, as many things are, and you can see the plot along the bottom, is that actually the net magnetizations are pointing in a bunch of different directions, even those that have been tipped into the transverse plane. And that's exactly the phenomenon that I was illustrating in the previous slide, that they'll be dephased, and the rephasing gradient there points them, more or less back together in the same direction. And you can see that by that little negative triangle GZ gradient in the diagram in the bottom left of these movies. And that's the level of detail we're going to go into. You can actually expand this in some other ways and use this concept of excitation K-space, which there's like a the concept of a K-space for RF pulses follows a very similar equation to our readout K-space, and this is a way to understand both this slice select rephasing gradient, as well as like some kind of crazy RF pulses like this, where you have a spiral type gradient, so we're doing gradients in X and Y during the RF pulse, and it turns out we can, instead of just exciting a slice, we can actually excite a cylinder volume too, with something like this. This is more for your knowledge and interest to look further if you like. Okay, so I want to switch gears and review briefly what's happening with our transverse magnetization during a gradient. And this is for the purpose of illustrating the effect of the 180-degree pulses. Okay, so in this illustration here, we have some time 1, time 2, time 3, and here I'm illustrating the accumulation of phase of the transverse magnetization due to the magnetic field gradients. So have a little slow accumulation, larger accumulations further away we get from the origin, and continued rotation over time. And hopefully this should be a review of some of the prior concepts we've covered. Now, there's this concept we've mentioned called the gradient echo, and I think this is very clearly shown in this type of illustration. Okay, where if we look at a time before a gradient, and look at these 4 times here. So what happens during the first interval is we apply a negative gradient, we'll get rotation, variable rotation as a function of position in one direction. Then when we reverse that gradient, we get rotation in the opposite direction. And at a certain time, we can cancel out the effects of prior gradients. Again, that's going to be when we have an equal areas here. And so this is when the gradients are going to cancel out from each other. And this is the time that is referred to as, this is the gradient echo, is when the effects of the gradient are canceled out, and that's where we usually define our echo time to be, is at in the case of the gradient echo sequence, the gradient echo. Now what happens in the case of 180-degree pulse? Okay, so we get, things start off the same. Now, the thing you may have seen in the pulse sequence diagrams, like the one I showed before, is we actually do the gradients in the same direction here. So this creates some direction of rotation dependent on position. Okay, fine, we've seen that before. Now what does the 180-degree pulse do? Just like was the case for refocusing phase due to off resonance, here we're just looking at the phase due to the gradients. It's going to flip around the phase due to the gradients. So the 180-degree pulse here. So it flips MXY, or it inverts the phase. So if at this time we're here at some angle phi 1, then at this time here, we're at an angle of negative phi 1, and this is true for anywhere in our object. And you can think of it as this pancake flip. We've tipped our spins, they've dephased, we'll flip them over, and by doing this, we've, or I can maybe draw it on here, these have been flipped this way, these end up getting flipped the other way, and we invert this phase. So then, to get our gradient echo, we can actually apply our magnetic field gradient in the same polarity and get the same, note the directions of rotation are always the same across all of these illustrations here. And so that means at some point when we have an equal area here and an equal area here, that at this point we would get it's going to correspond to this time here where everything's in phase. We get both what is illustrated at the bottom, we get both a gradient echo, and we also choose our timing of our gradients and our RF pulses such that the gradient echo and the spin echo coincide with each other. Okay, so this is because in K-space, most of our data is at the center of K-space. So we want to, or most of our information is there. So we want to have the spin echo refocusing occurring when we're near the center of K-space. Okay, so we choose them to be coinciding. But the other main point here is then how to handle the effects of the gradient or the phase when we have this 180-degree refocusing pulse in a spin echo sequence. And the key point here is that it flips or inverts this phase. Another way you can look at it, that is, this is a plot here from the book, is we can look at again the phase, and sometimes I denote this as phi x, where the actual the phase is like phi x times the position in x, and we get some net phase due to the gradient. There's a reversal of the phase of the 180-degree pulse, and then we can cancel that out with the same polarity of frequency encoding gradient. We get a gradient echo at some time where we have no phase. Okay. Now moving on to gradient spoiling, or sometimes known as crusher gradients. And these are another, that's referring to this gradient right over here. They sometimes draw in the pulse sequence. And there's another type of crusher gradient going to on the next slide, but this is sort of the an end of a TR gradient. And the purpose of this is illustrated in the net magnetizations here. So these three drawings are looking at time before, in the middle, and after this crusher gradient. And what this crusher gradient does is it takes our net magnetizations, which across our slice, are in phase. So we did our slice select refocusing, and it actually purposefully creates a lot of phase. So it purposely induces a bunch of rotation. And the reason for doing that is illustrated in the signal plot. So the average, or the signal averaged across our voxel, which is what we get in our image, that as we add more and more phase, in fact, the spins or the net magnetizations point in a variety of different directions, and when this happens, the signal across the voxel is effectively zero. Okay, so we have, and at the end of the TR, typically is what the case I'm showing here. Spins might be in phase. We're going to apply a bunch of phase. The purpose of this is to have no signal that carries over to the next TR. And this is typically done in the largest voxel size dimension. That's the place where it's easiest to get the most phase. Now there's another type of crusher gradients that you'll see in spin echo pulse sequences. And these are spin echo crusher gradients right here on the sides of the 180 pulse. And these can serve the purpose of illuminating signals when our refocusing flip angles are not perfect or not 180 degrees. And this almost always occurs, especially if we have slice selections, and slice profiles are not perfect rect functions. They have some, they're 180 degrees in the middle, they have some roll off at the sides. So I'm going to use to demonstrate what's going on here is this model simplifying things where we remove these slice selective parts of these gradients and just look at the effect of the crusher gradients. And this is the model we use over the next couple of slides to explain this. Okay, so as we have just discussed for gradients with spin echoes, if we have our normal pulse sequence behavior here, so meaning we have our ideal flip angles of 90 degrees and 180, if we look at the phase that is accumulated in the z direction, starts off nothing. This is interval 1 here. Then after the first gradient here, we accumulate some phase, and that's illustrated in the plots here on the right. And if we average across the slice, it's potentially destructive, like the other crusher gradient example. Now we're going to remember that what is our 180 pulse going to do? It's going to flip these or invert the phase. It's going to flip the net magnetizations around. So if we look at this phase diagram here, it's going to flip it around to the negative value here. So that's our time 3. And then what we've created at the end here is basically a gradient echo, or where we've refocused. We're going to choose equal areas for these two gradients. And so we're going to get to a point at the end here where we've canceled out the effects of these crusher gradients. And this is exactly what we want. We add these gradients in. We don't want them to have an effect when we actually have our ideal scenario, or this turns out this model applies for the spins that undergo the spin echo refocusing. This is okay. So anyways, everything is running at face value. These crusher gradients have no effect. So we're going to model 2 other scenarios that cover the cases where the flip angles are not where we're going to expect. They're going to look like the extremes, but they in fact are faithful representations of what can happen with the non-idealities. So the first case we can analyze is spin echo crusher gradients when we look at magnetization that might be excited by the first RF pulse, but not excited by the second RF pulse. And what's going to happen in this case is we're missing this flip, or this inversion of the phase due to the 180 degree pulse. So the situation here is the same as before. We don't have this flip of the 180 degree pulse. This is modeling the magnetization that again, is not affected by the refocusing pulse. And we're going to get like a ton of phase due to these crusher gradients. So what this is going to do is this effectively, sometimes the term that's used is spoil. And so it's going to spoil or crush this net magnetization. So the net magnetization that sees some excitation pulse but does not see any refocusing pulse. And you can see that by the end here at time point 4, just accumulated a ton of phase. We have that the crushing effect as we initially demonstrated it. And the final case we're going to look at is look at transverse magnetization that actually does not see the first RF pulse, but instead just sees excitation from the second RF pulse in our spin echo sequence. These approximations here, these simplifications, this model, in fact, cover the effects that we're trying to eliminate with the crusher gradients. So to do this, we have our flip angle set to be 0 for the first pulse, so something that a component or a net magnetization that remains longitudinal. And in fact, what that means is that it has no phase accumulation. Our gradients only affect our transverse components. So I'm not even going to draw this phase diagram until we get to after the RF pulse here. And then we're at time point 3 where we've took down our net magnetization in the transverse plane. And then this additional gradient introduces some phase across the Z direction. And so we're also going to spoil or crush this component. So taken together, the effect of these crusher gradients is effectively that only net magnetization that is going to be forming a spin echo will not be spoiled or not be crushed. The net magnetization that doesn't fulfill the conditions of a spin echo, so it doesn't see the first RF pulse or it doesn't see the second RF pulse, we actually don't want to image those components because they're going to have T2 star decay on top of them. They maybe at the edges of our slices or something. And so we spoil and crush these components. We only image the components that experience a normal, complete spin echo. So to wrap up here, I do want to go through kind of building on previous chapter, talk some more about characterizing the gradients and look at some of these from the K-space perspective. So if you recall, this is our definition of K-space, and what K-space is is basically the image phase, right? So it's the transverse magnetization. We have a T2 decay on that, and then this e to the I term with K in there is our phase. It's created as a function of K-space and or our gradients and a function of position. And we're usually going to make this approximation at the bottom that we're going to neglect T2 and just look at the effects of the gradients and the initial transverse magnetization. So here's an illustration of the K-space trajectory for a simple case of just applying an X gradient. And if you recall from the last chapter, sometimes we use this phi of X represent the phase accumulated due to the gradients, this is proportional to our case-based location. So in the previous examples, in this, particularly with the spin echo, we can simply replace phi of x by k of x, or ky, kz as well. And so here's the illustration of the gradient echo in k-space. And since k-space is this net gradient area, and again, when we have an equal area here and an equal area here, then we're going to get this gradient echo. And we're generally going to define this is kx of at our echo time, our gradient echo time, is going to be equal to 0. This is another way of saying we've unwound the effects of the frequency encoding gradient, and that's where we get this gradient echo where our net magnetizations are in phase. Showing that from the 2D perspective here, let's see as we traverse k-space, we're going to travel back through this center location, and again, this point here is going to be our, no, I can tell you this is going to be the echo time, or this is when the gradient echo occurs. And this applies whether or not we do phase encoding. So we're always going to use the frequency encoding gradient as our point of reference for our gradient echo. Now, another point to make here that was also shown in some of the spin echo examples was that the cumulative effects of gradients we can also look at in terms of k-space. And using this equation here, we see that the k-space creates this net rotation only when we have some transverse magnetization to begin with. Makes sense. Again, our gradients only affect rotation in the transverse plane. So if we put our gradient before our RF pulses, these should have no effect. And then I want to go through what things look like in the k-space perspective from a spin echo pulse sequence. So this is one way you could do and create a spin echo pulse sequence. Simply move all of our frequency encoding gradient past the 180-degree pulse, and we would get the same kind of evolution of k-space, and we'd hit our gradient echo and our spin echo. They're going to coincide. And this also, this is both the gradient and the spin echo. But as we showed before, we can create a spin echo, or you can get a gradient echo by reversing the polarity of that initial pre-winder gradient. That's sometimes what this is referred to here as the pre-winder. So, and the way we look at this in the k-space perspective is that since the 180-degree pulse inverts the phase of the transverse magnetization, and k-space is in this phase term of the transverse magnetization, this means the location in k-space is inverted by the 180-degree pulse. So if we're at some, value kx naught before the 180-degree pulse, afterwards we're going to be at opposite location negative kx naught. And then our positive gx gradient creates some positive slope in K-space. So we see we still get our gradient echo in this case. And this is just another way of looking at the example I showed earlier when we were looking at the transverse magnetizations, but now looking at things from the K-space perspective. Now from phase encoding gradient, so here note that I switched to GY and KY. We still get this inversion of the location. So if we were at some location KY naught before the 180, we get moved to a location negative KY naught after the 180-degree pulse. So we're going to need to keep, this manipulation of the K-space location again occurs on our various K-space directions corresponding to our different K-space axes. Okay, so to wrap up here, what have we covered? We've covered our slice select refocusing gradient. There's this little piece here, and that's to undo some phase that accumulates during this pulse, the slice selective RF pulse. We've looked at our spoiler gradients in the case of this 2D sequence. It's just one at the end of the sequence, but we also looked at the case where they're used in spin echoes. And then the K-space perspective, you can understand what's going on with this sort of pre-wind gradient, or what's happening at the end with these gradients is we're actually undoing, we're rewinding the effects of the gradients. And so you should be able to take a pulse sequence like this and understand and draw out the K-space trajectory for this. So, so you want to be able to describe the purpose of these, this slicer phasing, the crusher gradients, and the basic mechanism, and also how spin echoes affect the gradient's phase, or alternatively look at this from the K-space perspective. So how do the spin echoes affect our location in K-space? Great, thank you for watching.